Birthday?
You don't even know. So the HR director is out for the week with mono, and I have got to conduct the interviews for the new secretary position.
Oh man, how many do you have?
About 20. And of course, HR has all of these rules where I can't look at the resume beforehand, and after each interview, I have to either accept or reject them. I'm not a fortune teller. Goodness. And what if I don't choose the right one?
You know, this sounds like the secretary problem.
I know I have a secretary problem.
No, I mean the secretary problem. So it's a classic math probability problem that is based on the theory of optimal stopping. So basically it implements this stopping rule that maximizes the probability of getting some known reward.
Okay, so in our case, the reward is choosing the best candidate for the job while conducting the least amount of interviews?
Exactly.
Aha!
So basically it makes the following assumptions. The candidates will be interviewed in a random order. The quality of each candidate is independent. You are able to rank the current candidate relative to all the others that you have already interviewed. You must decide whether to accept or reject each candidate immediately after the interview. Once you have hired a candidate, you cannot see the rest. You can choose to stop interviewing at any time, but the candidate at that position may not be the best. If you get to the last candidate, you must accept him. You cannot recall any candidate that you have already rejected. The strategy for the secretary problem is to interview and rank the first R candidates, reject all of them, but remember the quality of the best one. Then we choose the first candidate after the Rth position who is better than the best of the R group. Our goal is to determine the optimal size of R that will maximize the probability of choosing the best candidate. The easiest way to conceptualize this problem is by looking at three groups. The largest group has size big N. This is just the total number of candidates or positions. The smallest group has size R. These are the candidates in positions 1 to R in which all of the candidates are definitely rejected. Therefore, R is our stopping point. The middle group has size N. These are all of the rejected candidates in the sequence. We assume that the best candidate in 1 to R is also the best candidate in 1 to N. Therefore, the lower bound of the value of N is R, and the upper bound is big N minus 1. This sets up the problem so that the best candidate is always at the N plus first position. We define random variable xi as the event that we choose the position of a candidate where the range of I is from 1 to big N. A is the event that we choose the best candidate. By the law of total probability, the probability of A is the sum of the intersections of the probability of A and xi. This is equal to the sum of the probability of A given xi times the probability of xi. The probability of choosing the position of a candidate is simply 1 over big N. The probability of winning, given that you've chosen a position, is R over little n, where n goes from R to big N minus 1. Therefore, our final equation for the probability of choosing the best secretary by implementing the stop rule is as it is shown on the screen. In order to optimize this equation, we need to take the derivative. We can convert this summation into a Riemann approximation to an integral as shown. By setting the derivative of this to 0, we maximize the probability of choosing the best candidate. Our final solution is 0.37. Therefore, our optimal strategy is to reject the first 37% of the applicants, remember the best out of these, and then choose the next candidate who is better than that one. Let's do an example. So let's say that we have a situation where there are 10 candidates. The red candidates are the ones that will definitely be rejected. The starred candidate is the one that has been ranked as the best relative to the other red candidates. The yellow candidates are the ones who are actually being considered for hire but do not outrank the starred candidate. The orange candidate is the first one that we see after the rejected ones who outranks the starred candidate. This is the one we hire. Therefore, the green candidates are the ones we never see because we have already filled the position. The reds constitute the first group, where the size of R equals 4. Once we have reached the fourth candidate, we have ranked all of the reds and have remembered the quality of the best one, which is denoted by the star. This is also the point at which our second group begins with size n equals R, or n equals 4, This is because we have set the condition that the best one in the first group from 1 to R is also the best candidate in the second group from 1 to N. We want to choose the best candidate at the N plus 1 position who is better than this candidate. As we conduct each subsequent interview, N increases by 1 until we reach the position before the first candidate who is better than the starred one. In this case, The value of n equals 7 because the best candidate is at the 8th position. It is important to note that if we had gotten to the 10th interview, we would have had to accept this candidate regardless of quality.
You know, you should really go tell your boss about this.
That's not a bad idea.
You might get a promotion.
Hey, hey, partner, here I come. Wait, did I say something? What's happening? Okay, I think I have found the right person for our secretary position.
Wow, so quick.
Yeah, I just used like a similar problem in which I reject the first few candidates and then accept the person that I feel is best after that.
Are you positive that it is a good method to use? I mean, what if the best candidate is in the first group that you interviewed and rejected?
Well, that wasn't in the secretary problem.
Well, I think it is a good idea to be able to, recall the people that you already rejected. Actually, I was going through the candidate list, and this person is my nephew's girlfriend's cousin. And then you already rejected him. Can you still hire him? Can you call him back?
I don't know how sure someone who we've rejected will feel if we call them back. And plus, I don't think at the end of the day it'll change our optimal.
Well, so if you suppose you've interviewed all the candidates in the second group but failed to find the ideal one who is better than the best candidate in the rejected group, the probability of recalling is 1 over big N. The longer it takes for you to go throughout the whole group, the probability of recalling a rejected candidate is lower. The probability of getting to big N plus 1 candidate is the same as all the other big ones, R over N. Adding that part into your summation, now the upper bound of the Raymond summation becomes big N instead of big N minus 1. Following the same method, surprise, we see that the upper bound of the integral is exactly 1 as opposed to approaching 1 as big N increases, which means the size of the candidate pool does not make a difference to the optimization process, and the optimizing point is still 0.37.
So at the end of the day, it doesn't matter or whether or not we added recall into the problem?
No, what matters is that my nephew's girlfriend's cousin gets hired.
Okay, we have a problem here. We have used our entire budget, and we have no budget for next year's recruiting season. What are we going to do about this? We have no money.
Guys, we'll have to keep in mind that it takes time and money to interview people. We'll have to pay for their hotel and their travel, and we'll have to pay for the recruiters to interview them. Okay, Jenny, why don't you go get my coffee? And Jackie, so let's tackle this problem.
So we suppose that each candidate brings in a certain amount of benefit in proportion to their rank of quality, and the cost of interviewing each candidate is a constant.
Exactly. We can express the net benefit of selecting any candidate in such mathematical equation. The first part is the benefit that the final candidate brings in, and the second part is the cost of the whole interview process.
In this case, we do not incorporate the stopping rule. So the probability of selecting each candidate is 1 over big N, and we can see that the expected benefit the selected candidate brings in would be a constant, and for the net benefit, we subtract the cost from the benefit, which is minus cost of interviewing all the candidates. Then we come to the conclusion that the best strategy is to select the first candidate so that we minimize the cost and maximize the net benefit.
Perfect. So in conclusion, in the original secretary problem, we reject the first 37% of the candidates. If we can recall rejected candidates, this does not change. In our penalty case, since the expected value would be the highest if we pick the first candidate, considering the cost of the whole interview process, we always selected the first candidate. Well, Jackie, since we're broke, just hire my nephew's girlfriend's cousin.